that should give us a tremendous factor against background in favor of the signal. In fact, a factor of about 1,000,000, 10 to the 6th. And that overcomes this factor of 10 to the 4 here. And we could, in fact, thank goodness, use a reactor to do this experiment. Well, to make this long story shorter, we called next morning, told Kellogg that we were calling off this experiment. We got our groups together, canceled all of our plans, and began a new set of work aimed at using a reactor. Now, in using a reactor to detect this reaction, this being the reaction that we're going to look for, one had to prove that this reaction occurred. One had to test each term in the reaction. Well, the neutrinos we could test by putting up so much shielding in front of us between our detector and the reactor that the only neutrinos could come through, and furthermore, they should only be coming through this shield when the reactor is running. So we should get a signal when the reactor is running and only background when the reactor is turned off. That would test the first term. The second term we could test by putting water and getting a signal, hopefully. Water or some organic substance containing protons, and get signals from this, and then replace that water by something else which physically is almost the same but which does not like neutrinos as much as protons do, and that turned out to be heavy water. So we could replace this light water with heavy water, replace the protons with deuterons, and deuterons don't like neutrinos as much as protons, and so the cross-section is about 1/30th that of protons, and so our signal should drop by that amount. The next term is the neutron. The neutron we know captures, as I've indicated, in protons, giving gamma rays, but it takes about 100 microseconds or so in water for that to happen. So we thought of adding something such as cadmium. Cadmium likes to absorb neutrons, but only when they're slow. These neutrons are emitted fast, they have to slow down, and we could add some cadmium as cadmium acetate or cadmium chloride or something to the water and capture these neutrons and then measure the amount of gamma rays that came off, and we should get about 8 MeV of gamma rays that came off. And as the neutron only captures when it's slow, if I draw this diagram of the rate of capture versus time, this is time following the appearance of the neutron, the fast neutron, and this is probability for capture. It would start off at very low probability, rise to a maximum, and then decay away. And one would have a neutron capture curve in time that looked like that. That would give us the delay between the pulse of the positron, which happened very quickly, and the capture of the neutron. Now, by adding less cadmium to the water, if it's a neutron, this curve should look perhaps like that. And by making more cadmium, higher cadmium concentration in the water, the curve would look like that. And we used computer simulations and could calculate quite accurately what this curve should look like, and so we should test then the fact that this is a neutron. Finally, the last term, the positron, is very characteristic. It always emits, almost always, when it captures with an electron, emits 2 gamma rays, and these 2 gamma rays are half MeV, or 0.51 MeV each. Furthermore, these 2 gamma rays go off in opposite directions from the site of this electron capture. So one had to just detect the fact that 2 gamma rays came off at opposite directions from the water and that they were half MeV each. Well, this then was the scheme. Finally, the last factor that came in to the to the story was the development of liquid scintillators. Crystal scintillators had been discovered some 10, 15 years earlier. Now liquids, certain organic liquids, had been found to scintillate. That is, when a gamma ray or an electron came through the liquid, they would excite. The gamma ray would produce an electron in any event, and the fast electron would excite the molecules of the organic liquid, and the liquid then would de-excite and emit some light. And the development of phototubes, which were so sensitive that they could detect down to 1 and 2 photons of light and detect them with high efficiency. These are called photomultipliers, and your instructor can, if he hasn't already done so, tell you about how a photomultiplier works, but it can amplify the current from 1 photon of light. It can produce a tremendous number of electrons at its output. So it's very sensitive. Well, liquid scintillators at that time had only been made in small quantities, a tablespoonful or so, but we needed large quantities. We needed tons. We wanted the liquid scintillator, in one instance, to supply the protons, or at least to give us so much detection volume that we could surround a large volume of water with this liquid scintillator. Well, our group, we had a very fine group of people at Los Alamos, including some chemists, other physicists and electronics people, and we found how to make liquid scintillator in large volume, and it can be made in arbitrarily large volume, and so one could then build a big detector. We made a first experiment, at Hanford, the Hanford Engineering Works, where the country's newest reactors were just going up, out in the state of Washington, and we came back having pushed the cross-section not to 10 to the minus 43 square centimeters, but we had an upper limit on that cross-section of 10 to the minus 39 square centimeters. And we were stopped at that point by the discovery of cosmic rays. Now, you thought cosmic rays were discovered a long time ago by other people. Well, they were. It's just that we discovered them again. We had completely ignored the cosmic rays, hadn't given them any thought. Turned out that the detector could be shielded from the reactor very well, but we hadn't shielded well enough from the cosmic rays. So we came back to Los Alamos in 1952, relayed our plans, rebuilt the detector, made it bigger, and then laid plans to go not to Hanford but to the Savannah River plant of the Atomic Energy Commission, where even larger reactors were just coming up to power, producing a very large flux of neutrinos, and we found that we got permission to get near one of them. And so we built the detector and took it down there and installed it in 1955. And the detector looked something like this. There was a thin layer of water, a few inches thick, in a large can of thin sides, this being water, so there's our protons, perhaps a ton of water. And then next to that water was a large can of liquid scintillator. So this is scintillator, and this is scintillator. And then a few hundred phototubes, photomultipliers on each end of this system. And now we had everything we needed. The water being in here, the neutrinos would come from the antineutrinos would come from the reactor. They would interact. There would be quickly the positron pulse coming from the annihilation of the positron. The neutron would be slowing down and wiggling around in this water as it slows down, and then capture in cadmium, and one would now have a burst of gamma rays coming from that capture and have the two pulses. Just to be doubly sure, we built this twice as big. We added another can of water here and another region of liquid scintillator down here. And so we had 2 detectors, and we had to require that these detectors would act exactly the same way, that the signals from each of these detectors, this triad, would be the same. Well, from there on, it was just work. It was fun. We worked about a year. We had calculated that the counting rate for this event should be about 3 or 4 counts per day. That's exactly what it turned out to be, within a few uncertainties. So it isn't exactly, it's approximately what it turned out to be. It turned out that it was twice too high from what we had calculated, but that was soon solved by, that problem was solved by the failure of parity, conservation of parity, which again I refer you to your instructors for, which doubled the cross-section. We waited for the reactor to turn down, to turn off, and the signal would disappear, and then the reactor would turn on again. They didn't do this for us, they just did this. Everybody there wanted to keep the reactors running as much as possible, but we'd walk around with long faces waiting for them to break down. They'd break down, and we'd be happy, and they'd say that we had put a jinx on them. So we'd get background counts. We replaced the water with heavy water with cadmium in it, and the signal dropped. We changed the amount of cadmium for the neutrons, and that changed the counting rate of neutrons. And finally, we put absorbers in between these sections and could check the fact that the gamma rays were in fact half MeV. Well, this was the observation then of inverse beta decay, catching the thief with the energy in his pocket away from the scene of his crime. Much has happened in the story of neutrinos since then. Not only do we have neutrinos such as I've been talking about, but we have other kinds called muon neutrinos, which again I refer you to your instructor for. And in fact, we're using neutrinos now to penetrate nuclei and nucleons at extremely short distances, and so probe the atomic forces and the constitution of the nucleon and of the proton itself. I thank you for your time, and I'll pause a moment to see if there are any questions. Say goodbye.